Financial Modeling, Topic 16, Options and Volatility, Section 6. We're going to compute and understand exponentially weighted moving average volatility, or EWMA. Now, the normal standard deviation and variance formulas compute a weighted average deviation from the mean, where each observation is weighted equally. So here's our formula. We're going to take the average squared deviation from the mean. So here's the observation in period t minus I minus the mean. That's the deviation from the mean. I'm going to square it. So think of having 100 days of data. So you have 100 squared deviations from the mean. And what you're going to do is simply take, say, 1 over 100, equally weighting each of the last 100 days. I then take the square root of that variance, and that gives me the standard deviation. So this is our standard or normal standard deviation formula. It's the square root of the variance, where the variance is the squared deviation from the mean, where each deviation is equally weighted. Now, research has shown that volatility is autocorrelated. In other words, calm is more likely to follow calm, and it's also called volatility clustering. So the exponentially weighted moving average is a volatility estimate that weighs the more recent data more heavily than older data when computing that volatility. In other words, if I had 100 days here, I'm going to weigh what happened yesterday more than 1 over 100, and I'm going to weigh what happened 100 days ago less than 1 over 100. So I need to find a scheme of weights that will weigh the more recent data more heavily. The solution to this problem is EWMA. But let's step back one more time. So here's the formula we just covered. When working with daily data, it is sometimes or usually the case that when we calculate daily data, when we're trying to figure out what the daily mean is on, say, a stock, it's going to be so small for daily observations. Sometimes we just assume that that number is 0. So this standard deviation formula simply collapses to this. It's the average squared deviation of squared return. Since the mean would be 0, it would be simply the squared return. And then I take the square root of that variance and get my standard deviation. So this is what we generally would do when having daily data. Calculate variance assuming the daily mean is 0. So if I want to get a different set of weights other than 1 over n, EWMA replaces that 1 over n vector of weights with this. 1 minus lambda times lambda to the I minus 1 over the sum of all those 1 minus lambda times lambda to the I j minus 1 factors. And what this lambda, it's going to be a constant, usually between 0.9 and 0.99. And it's a mathematical factor that affects those weights. That lambda is also called the decay factor in this model. So we're also going to estimate this for Google, and the first thing I need to do is have that lambda. Let me just tell you that this is a JP Morgan risk metric document from a few years ago, and they forecasted that when using the EWMA model of estimating volatility, 0.98 is the optimal lambda for US equities. So I'm going to use that, go to my spreadsheet, and show you how I did this EWMA model. So notice I have my continuously compounded returns. I then squared them. I then have my 1 minus lambda times lambda to the I minus 1. So notice when I take 1 minus lambda times lambda to the I minus 1, I could use a lambda of, say, 0.98. When I do that, the weight for the most recent day will turn out to always be 1 minus lambda. Let me make this a little bit bigger. And then what you see is these weights go down over time. And if I were to graph these weights, what you'd see is they'd go down exponentially fast. So these are my weights. I'm going to use 1 minus lambda times lambda to the I minus 1. And so on. The sum of those weights adds up to a number that's really close to 1. I can increase some decimal places. You can see it's really close to 1. However, when I look at the set of all these weights, they don't actually equal 1. And that's not a good property for a weighting scheme, because what that says it's going to do, it's going to actually factor down my data by a little bit. So the actual weight I'm going to use is not going to be this. I'm going to take that weight, which that 2%, and divide it by then 99.99, the sum of all of these weights, and I get something a little bit bigger. It's going to increase it. I'm then going to take that 2% over the 99% and multiply times the squared return. So what this is, I'm weighting the squared returns by 2 over 99. And then I'm weighting the prior day's squared return by 1.96 over 99, and so on. So these are the weights times these squared returns. If I sum that up, well, let me change the color of that. If I sum that up, that entire column, that's going to be my weighted average squared deviation from the mean, or my weighted average squared return. That is my EWMA variance. If I then take that EWMA variance, take it to the 1/2 power, turn it into a standard deviation, multiply times the square root of 252. That is my EWMA volatility using a lambda of 0.98. Now notice if I make that lambda say 0.94, I get 22.72. All right, the way in which you determine an optimal lambda is that you would take a stock and see over prior estimation periods what lambda historically has been the best to forecast future volatility. But we'll just go ahead and leave 0.94 in there for now. And using that model, I get 22.72 as my EWMA vol. That's weighting these more recent days more heavily. So in this topic, we calculated the EWMA, and the next topic we're going to talk about GARCH, but let's first talk about EWMA advantages. One of the main advantages, having done this in practice, is it uses all the data. You don't have a decision. Do I only use the last 1 year data, or 2 years data, or 3 years data? You can use all the data. It also matches the empirical observation of volatility clustering, or the autocorrelation of volatility, because it uses more recent data more heavily. And it's often used to forecast short-term volatility, say days or weeks. The main disadvantage of EWMA is it doesn't account for the second empirical finding that we've talked about when talking about volatility estimation, and that is there appears to be mean reversion of volatility. So there's volatility clustering, meaning if there's been a lot of high volatility days, it's more likely to have a high volatility day today. However, over the long run, it's going to probably more likely to return to the long-term average volatility. The solution to this problem is going to be our next model, which is going to be GARCH, which is basically EWMA with a mean reversion factor. But we'll get to that in the next topic. So in this topic, we calculated EWMA volatility, talk about its advantages. In the next topic, we'll calculate GARCH volatility.